We're ready to talk more in depth about inverse trig functions. We've talked about the thing that looks like sine to the -1. It's actually not sine to the -1, it's inverse sine. Or what's synonymous with that? What's the other way we can write inverse sine? Remember arc sine? That's the same thing. And instead of inverse cosine, we could write arc cosine, and that would be the same thing. We talked about the inverse trig functions just a little bit somewhere in chapter 5, but we're going to get some more details here. Let's graph y equals sine x, because anytime we're talking about the inverse of a function, we know that all the ordered pairs are just reversed, and we know that the graph of inverse sine should be the graph of sine just reflected with the line y equals x, or turned sideways. You know how x cubed is the increasing snake-shaped graph, and then cube root of x is just that turned horizontally? We should be able to do the same thing with the graph of sine to get the graph of inverse sine. So real quickly, our graph of sine, sine of 0 is 0, sine of pi over 2 is 1, sine of pi is 0, sine of 3/2 pi is -1, sine of 2 pi is back to 0. And we can go backwards with that as well. Sine of -pi over 2 is -1. Sine of -pi is 0. Sine of -3/2 pi would be back to 1. And sine of -2 pi is back to 0. So here are two complete periods of the graph of sine. Oops. They like that didn't have a square top. This is a function because it passes the vertical line test. Anywhere you put a vertical line on that graph, it's only going to touch the graph in one place, but it's not one-to-one because it doesn't pass the horizontal line test. There are infinitely many places you could put a horizontal line that would touch the graph in more than one place. You can't talk about the inverse of a function unless you restrict its domain to a portion over the graph for which the graph is one-to-one. Now, there are several different things we could use. We could use from -3/2 pi to -pi over 2. The function would be 1-to-1. Or from -pi over 2 to +pi over 2, the graph would be 1-to-1. So all the powers that be had to sit down one day and say, okay, what are we going to use for the restricted domain of sine so that we can talk about inverse sine? And I don't know if anybody disagreed and was stoned or not, but eventually everybody said, let's use -pi over 2 to +pi over 2. The fourth and the first quadrant. So to restrict the domain of sine to get just a one-to-one portion of the graph, we're going to use from -pi over 2 to +pi over 2. And some ordered pairs that are in that interval are, well, at -pi over 2, sine is -1. At 0, sine is 0. And at +pi over 2, sine is 1. What's the range of that function? Range refers to the y values. The lowest y value on the graph of sine is -1, and the highest y value on the graph of sine is +1. So you know all of these things about the graph of sine x You should be able to use this knowledge to graph inverse sine of x. When you see y equals inverse sine of x, or it could be written y is arc sine of x. I actually think that's a better notation because it doesn't look like a negative exponent. You need to think y is an angle whose sine is x. You give me a sine value. You give me the y value of some point on the unit circle, and I will tell you the angle that has that sine value or that y value. It's hard for me to take a portion of a graph and turn it sideways in my head. That may not be a big deal for you, but it is for me. So just reverse these ordered pairs and plot them. When you graph a function and its inverse, the ordered pairs are just reversed. On the graph of arc sine, you'll have the ordered pair -1, -pi/2. Still go through the origin, and it'll have the ordered pair +1, +pi/2. Something else you can remember about a function and its inverse, the domain of a function is the range of its inverse, and the range of the function is the domain of its inverse. That makes sense because all the ordered pairs are just reversed. The x's become the y's and the y's become the x's. So the domain of inverse sine is going to be the range of sine. That's going to be -1 to 1. And the range of inverse sine is going to be this restricted domain that we used for sine. -pi/2 to +pi/2. So to graph arc sine of x, we just need the -1 to 1 on our x-axis and the -pi/2 to +pi/2 on the y-axis. Pi/2 is about 1.5. So I'll try to make it look a little bit more than that distance. Here's +pi/2 and -pi/2. And plot these ordered pairs. -1, -pi/2, 0, 0, +1, +pi/2. If you're not careful, you could almost connect those with a straight line, but it's supposed to look just like this portion of the graph reflected with respect to the line y equals x. It doesn't look a whole lot different. And man, it's hard for me to get the curvature right. I almost can't do it without cheating, looking at my graph here, because I cannot take that little chunk of a graph and flip it with respect to y equals x to save my life. I would just die if my life depended on that. All right. Here's everything we need to know about sine, everything we need to know about arc sine. The domain of arc sine being -1 to 1 means we can only take the inverse sine of numbers between -1 and 1. If I say, what's the angle where sine is 2? Well, 2 is not a y value on the unit circle. The biggest y value on the unit circle is 1, and the smallest is -1. So if I say, what is arc sine, and then I give you a number that's outside the range or the domain of -1 to 1, It's just undefined. And this range being negative pi over 2 to positive pi over 2 means y equals inverse sine of x will always return a value, or let's say return an angle between negative pi over 2 and positive pi over 2, which is quadrant 4 or quadrant 1. The inverse sine button will always give you an angle between negative pi over 2 and positive pi over 2. So let's look at these properties of sine. I actually have them right here. That's page 4 from page 462 in the book. When you see the equation y equals inverse sine of a half, you need to think of what that means. That means give me the angle whose sine is 1/2, and the answer has to be between negative pi over 2 and positive pi over 2. See, there are 2 times on the unit circle where sine would be positive 1/2. Once in the first quadrant, let me try to reverse this, once in the first quadrant and once in the second quadrant. But inverse sine is never going to give us an angle in the second quadrant. So we've got to find the first quadrant angle whose sine is 1/2, and that's pi over 6. Inverse sine of negative 1/2, well, there are 2 angles whose sine is negative 1/2. One is in the fourth quadrant and one's in the third quadrant. Which one is inverse sine going to give us? The one in which quadrant? The third or the fourth? What did you just write? Right here. Inverse sine is always going to give us a first or fourth quadrant angle. It's never going to give us a third quadrant angle. So we need the fourth quadrant angle where sine is negative 1/2, and that's negative pi over 6. Now, negative pi over 6 is the same as 11/6 pi, but we have to write the answer as an angle between negative pi over 2 and positive pi over 2. That's why we write the angle as negative pi over 6 instead of 11/6 pi. Inverse sine of 1, there's only one angle in the unit circle whose sine is 1, and it's pi over 2. Arc sine of 0, there are 2 times on the unit circle where sine is 0. What 2 times? 2 angles that have a sine value of 0. Zero and 180 or 0 and pi, but only one of those is between negative pi over 2 and positive pi over 2. So y equals 0 is the solution. And then arc sine of negative square root of 3 over 2. There are 2 times on the unit circle where arc sine is negative, but arc sine's only going to give you the fourth quadrant angle where sine is negative square root of 3 over 2, and that's negative pi over 3. So this is just to illustrate that your answer always has to be between negative pi over 2 and positive pi over 2. Now, these properties have to do with the undoing nature of a function and its inverse. When you see sine of inverse sine, you want to go, well, they just undo each other and always leave you x. That's true as long as x is a number between negative 1 and 1. But if x is not a number between negative 1 and 1, then you can't find the inverse sine of x. So this first property only works for x's between negative 1 and 1 because you can't take the arc sine of anything else. The second property, inverse sine of y, those two should undo each other and leave you y, but they only will if y is a fourth or first quadrant angle, because that's all that inverse sine will ever give you. Now, let's see how to apply those properties. Page 511, number 2. The A part is inverse sine of -1/2. Now, this is just going to take a little practice, but when you look at that, you have to think the angle whose sine is -1/2. I'm thinking, well, sine is negative in 2 quadrants. Which 2 quadrants? Third and fourth, but which one will inverse sine give us? The fourth quadrant. So we need the fourth quadrant angle whose sine is -1/2. Now, until your mental imagery gets really, really good, you may have to draw it. The angle whose sine is -1/2. Is that going to be closer to the x-axis? Would y be close to a half, or the y-axis? It's right here, where sine is -1/2. So if this is -pi/2, this is 0, and this is pi/2, and my answer has to be written as an angle between -pi/2 and +pi/2. What is this angle? Yep, -pi/6. After you practice a bit, you don't have to draw the picture, but you still can anytime you need to. 4a is arcsine of 0. And I'm thinking the angle whose sine is 0. The angle has to be between -pi/2 and +pi/2. Where in that interval is sine 0? Yep, on the positive x-axis. 6a is arcsine of pi/2. Squint really hard and tell me the angle whose sine is pi/2. Well, you're giving me sine of pi/2. Sine of pi/2 is 1. I want the angle whose sine. The angle whose y value is pi/2. What's the approximate value of pi/2? 1.5-ish, 1.57. When on the unit circle is the y value 1.57-ish? Not gonna be, because the absolute highest y value on the unit circle is 1, and the lowest is -1. So don't be thrown off just because that has a pi in it. Ooh, it must have an answer. This is greater than 1. So that's undefined. (8a), the inverse sine the sine of inverse sine of 2/3. This goes back to those properties. You can only say sine and inverse sine undo each other if this argument is a number that you can take the inverse sine of. Could you take the inverse sine of 2/3? As long as it's a number between -1 and +1, yes, you can. And so if you can take the inverse sine of 2/3 and you find it, and then you take the sine of that number, those should just undo each other and leave you the 2/3. But if this had been sine of inverse sine of 3/2, could you take inverse sine of 3/2? No. You'd have to say, well, you'd have to say something else, but hang on just a minute. That's coming up in another problem. 10a. Arc sine of sine of -π/2. To say that arc sine of sine undo each other and just leave you the argument has to be an answer that arc sine can actually give you. Can arc sine actually give you the answer -π/2? Yeah, it's always going to give you something between, including -π/2 and +π/2. So just ask yourself, can that be an answer to arc sine something? If it can, then that's your answer. They undo each other. But in number 12, that's not going to happen. Inverse sine of sine of 2/3 pi. It's tempting to see inverse sine of sine and automatically say they undo each other and leave you 2/3 pi. But in what quadrant is 2/3 pi? It's in the second quadrant. Can inverse sine give you a second quadrant angle? No. So they don't undo each other and just leave you 2/3 pi because inverse sine cannot give you a second quadrant angle. In that case, you have to find the sine of 2/3 pi. 1626346. What's the value of sine right there? Square root of 3/2. So you have to find the inverse sine of square root of 3/2. We're just putting the value of sine of 2/3 pi in place of sine of 2/3 pi, and then find the angle that has that same y value, but is in the fourth or first quadrant. What's that angle that has the same y value in the fourth or first quadrant? Pi/3. So in this case, inverse sine of sine didn't undo each other because this wasn't an answer inverse sine could give you. However, you could find the value of this angle and then find an angle whose sine is that, but is in the range of inverse sine. I'm not understanding yet. Let me try again. I'm not flipping anything. Let me just repeat it, Chris, and if I don't say it better or if I don't say it the way you understand it this time, I'll try something different. I want to say these just undo each other and leave you 2/3 pi. But I know that 2/3 pi is not an answer that inverse sine can give you because it's in the second quadrant and inverse sine always gives you fourth or first quadrant. When that happens, I can't say they undo each other, but I can evaluate the sine of 2/3 pi. The sine of 2/3 pi is square root of 3/2. It's like I called that ugly and then put the value of ugly in its place. And then I could still take the inverse sine of that number. The angle whose sine is the same thing, but is in the range of inverse sine, which is fourth and first quadrant. That's difficult. I've done it enough now that it comes pretty easily to me, but it didn't the first time I did it. It did not come easily at all. All right. I want you to try 1 through 11, but in order to do that, tell you we still have, 3 minutes? Let's get this graph of inverse cosine down real quickly, and then I'll finish writing down that homework for you. Y equals cosine x. We know cosine of 0 is 1, cosine pi over 2 is 0, cosine of pi is -1, cosine of 3/2 pi is 0, cosine of 2 pi is back to 1. So here's 1 period of the graph of cosine, and we know that it repeats. But even with just that 1 period, the function's not 1-to-1. It doesn't pass the horizontal line test. So we're going to have to restrict the domain just like we did for inverse sine. It's logical to pick out a 1-to-1 chunk of that graph. It's 1-to-1 from 0 to pi. So let's use that for the restricted domain. And some ordered pairs in that domain would be 0, 1, pi over 2, 0, and pi -1. So what's the range of cosine? Range is lowest y value to highest y value. That's -1 to 1. Inverse cosine or arc cosine would have the same ordered pairs, but the x's and the y's are interchanged. So 1, 0, 0 pi over 2, and -1 pi. The domain of arc cosine is the range of cosine. You can only take the inverse cosine of numbers between -1 and 1. If I say, what's the inverse cosine of 7? It's undefined because 7's not between -1 and 1. The range of arc cosine is going to be the domain, the restricted domain of cosine. So I just need the 0 to pi on the y-axis and the -1 to +1 on the x-axis. And then plot those 3 ordered pairs. 1, 0, 0 pi over 2, about right there, and negative 1 pi. I can't take that chunk and flip it with respect to the line y equals x, but I can connect these dots. That's what the graph of inverse sine would look like. All right, got this one note, and then we'll go. The range of inverse sine is 0 to pi means, did I say inverse sine? I didn't mean to. I don't know what I said. I meant inverse cosine. Will always return an angle which is quadrant 1 or quadrant 2.
On page 464, there are some properties of inverse cosine similar to what we saw for inverse sine. When you see the expression y equals inverse cosine of a half, not only do you have to think, I'm looking for the angle whose cosine is a half. On the unit circle, there are two angles where cosine is a half. Beyond that, you have to think, and the angle has to be between 0 and pi. If you're looking for the angle whose cosine is a half, and you want the angle between 0 and pi, then there's only one solution, and it's pi over 3. There are also two angles that have cosine being negative 1/2. Cosine would be negative 1/2 in the second quadrant, and cosine would be negative 1/2 in the third quadrant. But we have to have the second quadrant angle where cosine is negative 1/2, and so there's only one solution. It's y equals 2/3 pi. There's only one angle whose cosine is 1 and is between 0 and pi. That's when y is 0. At 0 radians, your x-coordinate is 1, and so cosine of 0 radians is 1. When you see y equals arc cosine of 0, you have to think the angle whose cosine is 0. There are two angles whose x-coordinate are 0. That's at pi over 2 and at 3/2 pi. But if we can only choose the angle between 0 and pi, then there's only one solution, pi over 2. So you can see how those are analogous to the properties that we had for sine. Let's do the B part of number 1 through 11, since we already have the A parts done. On number 2, I think I had a typo there. I changed it. It didn't look like inverse cosine. It looked like cosine minus 1. But inverse cosine of negative square root of 2 over 2 means I'm looking for an angle between 0 and pi. Has to be an angle between 0 and pi, where cosine is negative square root of 2 over 2. Well, we know cosine is negative square root of 2 over 2 at the multiples of 45 degrees. So here would be the second quadrant angle where cosine would be negative square root of 2 over 2. And that would be 135 degree angle, or 1/4, 2/4, 3/4 pi is the angle whose cosine is negative square root of 2 over 2. On number 4, we're looking for the angle whose cosine is negative 1. You've got to Remember, we're looking for an x value being -1. Where in the unit circle would the x be -1? Well, right here at pi radians. X is -1, y is 0. So arc cosine of -1, the angle whose cosine is -1, is pi. Number 6, we're looking for the angle whose cosine is pi over 3. Now the most common mistake here is to just find to find cosine of pi over 3. Pi over 3 is 60 degrees, and I can tell you what cosine is right there. But I'm not looking for cosine of pi over 3. I'm looking for the angle whose cosine is pi over 3. The angle whose x value is pi over 3. Is pi over 3 the x value of any unit or any angle that we have memorized on the unit circle? No, none of our x's are pi over 3. As a matter of fact, all of our x's on the unit circle are between -1 and +1. What do you know about pi over 3? 3.14-ish divided by 3. Well, that's similar to the a part. Pi over 3 is a little bit bigger than 1. So there is no angle whose cosine is bigger than 1. And we say arc cosine of pi over 3 is undefined. In numbers 8, 10, and 12, we're using those properties of cosine. I would like to just say cosine and inverse cosine undo each other and leave you -1/5. But to do that, I have to make sure that -1/5 is a value of cosine that you can get on the unit circle. Actually, I said that incorrectly. Let me fix it. In order to say cosine and inverse cosine undo each other and just leave you -1/5, you have to be able to take the inverse cosine of -1/5. Can you take the cosine of -1/5? You can take the inverse cosine of any number between -1 and +1. So yes, you can take the inverse cosine of -1/5. And then the cosine of that angle would be -1/5. This is some angle whose cosine is -1/5. We don't know exactly what that angle is, but there is an angle whose cosine is -1/5. So if I was pointing at it and I said, hey, what's the cosine of that angle? Well, it would be -1/5. In the B part of number 10, I'd like to say arc cosine of 0 is 0. I'd like to just say they undo each other. But before I can say that, I have to think, is 0 an answer that arc sine can give me? Arc cosine always gives me a value between 0 and pi, inclusive. So is 0 a reasonable answer for arc cosine of something? Yes. Arc cosine can give you 0 as an answer. On number 10, that was number 10. Number 12, the B part, I'd like to say inverse cosine of 4/3 pi is just 4/3 pi. I'd like to say they just undo each other. But is 4/3 pi an angle that arc cosine can give me? Well, arc cosine can only give me angles between 0 and pi, so 4/3 pi cannot be the answer to this question. Like we did on the A part, I have to think about where 4/3 pi is. 162636465667676 is right here. And that's not an angle that inverse cosine can give me. That point on the unit circle is x is negative square root of 3, no, x is, my picture's not to scale at all, but right there x should be negative 1/2, y should be negative square root of 3 over 2. So cosine of 4/3 pi is negative 1/2. And then I can find the inverse cosine of negative 1/2 would be the same angle, but in the second quadrant, because inverse cosine can only give me an answer between 0 and pi. In the second quadrant, the angle that would have the same cosine, if I'm near the y-axis here, it would be near the y-axis here. And that is 2/3 pi. At 2/3 pi, x would be negative 1/2, cosine would be negative 1/2, and it's an angle that inverse cosine can give me, an angle between 0 and pi. All right. Let's go back to our notes and finish up this description of inverse tangent. And then we'll finish up 1 through 11, and that's where we'll stop. That's where the homework will stop for today. All right, inverse tangent. I know that tangent is sine over cosine. So it has its vertical asymptotes wherever cosine is 0. That's where the x coordinate is 0, and that is at the odd half pi's. When we first talked about inverse tangent, we said we will just use the period of tangent from negative pi over 2 to positive pi over 2. And we said between its asymptotes, tangent kind of looks like x cubed. It approaches those asymptotes. Tangent of quarter pi is negative 1. Tangent of negative quarter pi is negative 1. Tangent of positive quarter pi is positive 1. So tangent is 1-to-1 from negative pi over 2 to positive pi over 2. And some ordered pairs in that interval. Well, we just said at negative pi over 4, tangent is negative 1. At 0 radians, tangent is 0. And at positive pi over 4, tangent is positive 1. So what's the range of tangent? I know we're going to use for the domain negative pi over 2 to positive pi over 2, but the range is how low does it go, how high does it go. Tangent goes from negative infinity to infinity. So to graph inverse tangent, I just need to think these two functions are inverses of each other. That means all of their ordered pairs are reversed. Instead of negative pi over 4, negative 1, the graph of inverse tangent will have negative 1, negative pi over 4. And the ordered pair 0, 0. And the ordered pair 1, pi over 4. And because the graph of inverse tangent is the graph of tangent reflected with respect to the line y equals x, wherever tangent has vertical asymptotes, inverse tangent is going to have horizontal asymptotes at negative pi over 2, positive pi over 2. Horizontal asymptotes at positive pi over 2 and negative pi over 2. Here's the ordered pair 0, 0. Here's negative 1, negative pi over 4, and positive 1, positive pi over 4. You could just about connect those with a straight line, but if tangent is not a straight line, inverse tangent can't be a straight line. If you flip x cubed along the line y equals x, what will it look like? The inverse of x cubed is cube root of x, and that's kind of what inverse tangent looks like. Its domain is the range of tangent. You can take the inverse tangent of anything, and when you write the domain is negative infinity to infinity, really you should have parentheses instead of brackets there. You can take the inverse tangent of all real numbers. The range of inverse tangent is the domain of tangent, and we said for the domain we're going to use from negative pi over 2 to positive pi over 2, which means that inverse tangent always gives me an angle between negative pi over 2 and positive pi over 2, and that would be quadrant 4 or quadrant 1. We're just labeling 3/2 pi by its other name, or by another name, negative pi over 2 to positive pi over 2. Inverse tangent always gives us an answer in that range. And then for our properties of inverse tangent on page 466, the first property just says tangent of inverse tangent or tangent of arctangent, same thing, they always undo each other because you can take the inverse tangent or arctangent of anything, negative infinity to infinity. We could only take arc sine and arc cosine of numbers between -1 and 1, but we can take arctangent of any number, and therefore we can say tangent of arctangent always undo each other for every x. When I exchange the functions and have the inverse tangent of tangent, then I just have to say inverse tangent and tangent undo each other and just leave me the y value, as long as that y value is an answer that inverse tangent can give me. Inverse tangent can only give me numbers between -π/2 and +π/2. So let's do this C parts of 1 through 11 and call it a day. Number 2, the C part says the angle whose tangent is -1. Well, I know tangent is 1 at multiples of π/4 because the x and the y are the same, or they're opposites of each other. So tangent's either +1 or -1 at all the multiples of π/4. I want the angle whose tangent is -1. Well, that happens in the second quadrant, and it happens in the fourth quadrant, where you have a negative divided by positive, or a positive divided by a negative, or a negative divided by a positive. This is 3/4 pi, and this is 7/4 pi. Which one can be the answer to inverse tangent? Well, actually neither one of those, because inverse tangent, I'm not going to write those fourth quadrant angles as 7/4 pi. I have to have an answer that's between -π/2 and +π/2. So what's another name for that 7/4 pi if I was counting clockwise instead of counterclockwise? Another name for this angle would be -π/4. Halfway through the fourth quadrant going clockwise instead of counterclockwise. Inverse tangent of -1 is -π/4. Number 4, arctangent of 0. I'm looking for the angle whose tangent is 0. The angle that if you divided the y coordinate by the x coordinate, you'd get 0. Well, I'm pretty sure it's going to have to be one of the quadrantal angles. Tell me whether it is 0 radians or π/2 radians, where the y divided by the x would give me 0. At π/2 radians, the y divided by the x would be undefined. It's at 0 radians that the y divided by the x would give me 0. All right. C part of number 6 says, give me the angle whose tangent is the angle whose tangent is -√3/3. I have to think of the angle which if I divided the y by the x, this is what I would get, and it has to be an angle between -π/2 and +π/2. In in these two quadrants, quadrant 1 and quadrant 4, which one's going to have an angle whose tangent is negative? It would have to be the fourth quadrant angle. And with that square root of 3 in there, I'm pretty sure it's either going to be negative pi over 6 or negative pi over 3. At negative pi over 6, the x just left being 1. The x is square root of 3 over 2. The y is negative 1/2. And at negative pi over 3, the x is 1/2 and the y is almost negative 1. So which one of those, if I divided the y by the x, would I end up with the square root of 3 in the numerator? I'm dividing the y by the x. I'm going to flip the x. If I had negative 1/2 times the reciprocal of the x, the square root of 3 would end up in the denominator, but when I rationalize that, I would get the exact value I was looking for. The angle whose tangent is negative square root of 3 over 3 is negative pi over 6. Because this y divided by that x gives me negative square root of 3 over 3. Number 8. I'd like to say that tangent and inverse tangent just undo each other and leave me negative 9. But before I can say that, I need to say, is negative 9 a number that I can take inverse tangent of? What's the domain of inverse tangent? What could I take the inverse tangent of? We said a minute ago we can take inverse tangent of all real numbers. So tangent of inverse tangent of negative 9 is negative 9 because negative 9 is a number that I can take the inverse tangent of. Number 10, I'd like to say arctangent and tangent just undo each other and leave me pi over 4. But before I can say that, I have to ask, is pi over 4 an answer that arctangent can give me? Well, arctangent, remember, can only give me answers between negative pi over 2 and positive pi over 2. So is pi over 4 an answer that arctangent can give me? Yes, it is. So arctangent of pi over 4 is pi over 4. And then one more. The C part of number 12 says inverse tangent of 7/6 pi. I would like to just say those undo each other and leave me 7/6 pi. Is 7/6 pi an answer that inverse tangent can give me? Well, 7/6 pi, if pi is 6/6, then 7/6 is right here. Is that an angle that inverse tangent can give me? No, it's not between negative pi over 2 and positive pi over 2. So it can't be the answer to this problem. But there is an angle 7/6 pi, and I can figure out what tangent of that angle is. This ordered pair close to the x-axis, the x is almost negative 1 the y is -1/2. Third quadrant, both coordinates are negative. Closer to the x-axis, x is closer to -1, y is -1/2. So tangent of 7/6 pi is -1/2 divided by -√3/2, or -1/2 times -2/√3. That's just positive √3/3, again, if we rationalized it. So where's the angle that has the same value for tangent, but is between -π/2 and +π/2? If at 7/6 pi tangent is positive, then there's also an angle in the first quadrant where tangent would have that same positive value. And if in the third quadrant, this is 7/6 pi is close to the x-axis, I really made that look more like pi/4. Then at pi/6, you would have the same ordered pair, except for the x and the y would both be positive. And a positive divided by a positive would give you the same value for pi/6 as we had for 7/6 pi. So I had to give the angle whose tangent is the same thing as the tangent of 7/6 pi. All right, like I said, this is not easy. This was not easy for me the first time I did it. Drawing pictures of the angles that I am looking for is very, very helpful to me. When I first started, I couldn't just squint until I figured out the angle whose tangent was -√3/3. I had to say, if tangent's negative, then it's either in the second or the fourth quadrant. Arctangent can't give me second quadrant angles, so it must be in the fourth quadrant. And it's either going to have to be at -π/6 or -π/3. I had to write down the two ordered pairs and see which one, the y divided by the x, would give me this value that I was looking for. So that's tremendously helpful to me, and I think it would be to you as well. All right, this is where we're going to stop. It's a good stopping point because you can see that number 14 is going to be different. Number 12, we were taking the inverse sine of sine, or number 8, we were looking for the sine of inverse sine. But number 14, we're looking for the sine of inverse tangent. That's going to take a little bit more work, and we've worked hard enough for today. So the homework's just 1 through 11 odd. Have a great day.